The second day of the workshop on QCD phenomenology. I have the honor to chair the first session of today. And the first speaker is Chun Shen from Wayne State University in RBRC. And you can see the title of his presentation already up. And Chun, take it away.
Okay, thank you very much. I will first thank the organizer to invite me to give an overview about the recent progress in dynamical description of heavy ion collisions. So let me start with general pictures of what we think about is happening in heavy ion collisions. So we accelerate two heavy nuclei to very high velocities and then collide with them. The system will undergo through a fast and pre-equilibrium stage and reach near thermal equilibrium about 1 Fermi over C, at which time the system can be described microscopically as a fluid and expands in free space. The system will go through a coagulon plasma phase down to a hadronic phase, and then eventually the system becomes dilute and particles stop interacting with each other and fly free to the detectors. So the whole important dynamics happens on a time scale of about 10 Fermi over C, which if you transfer back to seconds will be around 10 to the minus 23 seconds. So it's really fast for dynamics to happen in heavy ion collisions. So as you can see from this cartoon, there are several stages of these heavy ion collisions, which actually needs us to build up a multi-stage framework to actually describe physics at different length scales in different phases. So why is heavy ion collision important? So we use heavy ion collision to actually probe and extract properties of the hot QCD matters. And the important phase we would like to define is this coagulon plasma phase, which is a novel state of matters in addition to the liquid, gas, and solid phase that we usually know in our daily life. So the question we'd like to ask is how we can use the wealthy of the heavy ion data from all these colliders to identify or to quantify like the equation state for the hot QCD matter in this deconfined phase. For example, we'd like to know how temperature, so how energy density, pressure, and speed of sound behave as a function of temperature and the chemical potentials, whether there's a critical point, and also the phase transition between QGP and hydrogen gas will be first order at some place. We, in the past decades, we already learned a great lot from the lattice QCD for this equation state at mu b equal to 0. But we would like to extend our knowledge to finite mu b, as I will discuss in the following slides. In addition to equation state, we would also like to understand the initial state fluctuations for heavy ion collisions, for example, the initial energy momentum tensors, and also conserved charge currents in these heavy ion collisions. We also would like to know not only the thermodynamic properties, but also transport properties like shear bulk viscosity, or the transport energy momentum through media and also other probes. So I also list some selective experimental measurements that actually are sensitive to these aspects of these properties. But in realistic case, we really need to use multiple data to constrain all these properties at the same time. So it's not a one-to-one mapping, but that's actually very complex relations between the theory and the experimental extractions of these properties. So for heavy ion collisions, as I mentioned in the first slide, we need to develop a multi-stage theoretical framework, which usually is denoted as hybrid. So it actually involves basically a few stages, which is listed here. So we need to have initial state models plus some pre-equilibrium dynamics to model how the system is approaching from the impact of the two nuclei to near thermal equilibrium. And this is basically discussed yesterday by a lot of speakers, which happens about 1 Fermi over C. After that, we will have a dominant microscopic fluid dynamic phase evolving the system from 1 to about 10 Fermi. And then at the late time or the dilute phase, we'll usually switch to the hadronic transport approach, which we describe the collisions and decays of the individual particles microscopically. So the idea of this hybrid framework is trying to understand the evolution of the system's energy momentum tensor from t equals 0 plus to the end of the collisions. So basically, when we switch from one type of models to the other, we ensure that the system's energy momentum tensor is continuously mapped from one phase to the other. For example, in the early stage, from the pre-equilibrium dynamics to hydrodynamics, we ensure that the energy momentum tensor is conserved. And this is implemented by so-called Landau matching conditions to map the initial energy momentum tensor to flow variables. And this also needs the help of equation state to determine the thermal energy density as well as pressure in these procedures. At the late stage, when we switch the microscopic fluid cells into particles, we usually use so-called Cooper-Frye particleization prescriptions to basically map energy momentum tensor into particles. But the key idea here is that we need to ensure that the system's energy momentum tensor is mapped continuously between different phases. So the main role of this hybrid approach is using the hydrodynamic descriptions. So the hydrodynamics is a very universal, effective descriptions of the strongly interacting systems. It's based on basically conservation law of energy momentum tensor as well as charge current, charge densities, plus the equation state telling us what is actually the matter underneath we are solving, evolving. So hydrodynamics has been applied to a large variety of interacting systems. If on the large scales, you can actually simulate how the star forms in the universe by using hydrodynamics. In our daily life, you want to design a car or the shape of the car to be more efficient or kind of have high speed. You need to model the aerodynamics using hydrodynamics of equation motions around this car. We also, in our field, we use hydrodynamics to describe the strongly interacting system and interactions between heavy ion collisions. So I want to point out that the heavy ion collisions involve relativity because the energy is very high. We need to develop a causal and a relativistic hydrodynamics, including viscosity, because this is important transport properties that we like to study in quark-gluon plasma. So our field is actually leading the theory development also in trying to develop such a hydrodynamic framework, which is not essentially needed if we want to consider about the daily dynamics of in our daily life. So, so as I said, the equation motion of hydrodynamics need to be solved with equation state. In our context of how QCD matter, we actually use a QCD equation state calculated from the lattice QCD method. So, so here I show you a comparison of the so-called trace anomaly, which is energy density minus 3 times the pressure. So if the system is conformal, this trace anomaly will be 0. And it is non-zero at the finite temperature in QCD. And you can see that this the green and red band underneath the curve are the continuation extrapolation from the lattice QCD calculations in the recent year around 2014. The early parameterization of equation state around the year 2010 is indicated at this blue dash line. As you can see, that the modern equation state, which is listed as other equation state here, actually follow the continuum lattice QCD data once they are available. And you can see that more or less they actually converge to this within this band. And here on the right is the speed of sound square as a function of temperature for these different equation state compared to the lattice continuum extrapolations in this plot. So The key point here is that there's a few equation states that are available on the market that has been used by different hydrodynamic codes. And more or less, they actually represent within the uncertainty of the lattice continuations that within this lattice continuum results. And there are still different version of that differ a little bit from each other. But if you are interested in how it influenced the observables, you can read our paper, which we basically do a small test, a simple test of these different type of equation state. So with these ingredients, we can actually solve hydrodynamic equations. In a nutshell, if you want to think about hydrodynamic equations, you can think about the acceleration of the fluid velocities on the left-hand side is driven by a pressure gradient divided by the system's entropy. So this equation can be basically understood as a Newton's second law, where you interpret the pressure gradient as a sum of that force divided by the system's inertia, which is represented by the system's entropy. What the hydrodynamic does is basically transform the spatial inhomogeneities into flow velocity, as indicated in the right-hand side of the movie here. So basically, as you evolve from hydrodynamic equations, the numerical solver basically translate the pressure gradients into flow velocity and expand the systems in real time. So the effects of viscosity can be actually understood in these slides. For example, here I would like to show you the effects of shear viscosity inside heavy ion simulations. So the viscosity eta here is proportional to the gradients of the flow velocity. It basically acts as a resistance to the shear deformations of the fluid. So if we now evolve energy density configurations in a semi-peripheral collisions, indicated as this overlapping area between the two nucleus. So on the left-hand side, I will show you the evolutions with no viscosity. On right-hand side will be with viscosities. So as system evolves, as you can see that the general feature you can immediately notice is that with viscosity, the profile become much smoother, or the energy density become much smoother at the late time compared to the ideal hydrodynamic simulation where viscosity taken to 0. You can still see there are some fine structures inside this fluid. So intuitively, you would understand this as that the viscosity will actually smear out the fine structures inside the fluid patterns in different angles. And the flow anisotropy that can be measured in experiments actually can help us to understand the size of viscosity in this fluid. So this flow anisotropy actually can be measured in experiments. So here are a few event display from the CMS event display detectors for different individual heavy ion collisions. And clearly you can see that for these energy depositions in the transverse plane as a function as a Musso angle, different events will have a preferred energy depositions along some axes in these events. And this basically determines so-called event plane. And then as the Musso distributions of this energy or particle numbers can be actually performed. We can perform Fourier transform to these distributions and extract these coefficients called VNs, which usually is called the anisotropic flow coefficients in our field. And these VNs actually help us to understand the deformations of the momentum distributions in the measurements. So all these VNs actually can form a called power spectrum, analogous to the power spectrum analysis if you look at the cosmic microwave background. So different from the cosmologies, we cannot do a Fourier analysis up to say moments of 2,500. We only, in our case, we can only get the non-zero values, a significant non-zero values up to say n equals 6 or 7 in our field. This is mainly because we have a very large viscosity, which damp the systems, the angular distributions very quickly. And also we are limited by finite statistics for each event so that we cannot measure too well of the higher order harmonics. But nevertheless, if we look at these different order harmonics from these final measurements, we actually can learn about the initial state fluctuations in the density distribution, as well as the transport properties through these hydrodynamic solutions, which convert this inhomogeneity into the momentum anisotropies in our systems. So here is one example of applying these hybrid simulations to a variety of the collision systems at the RIC and LC with one single set of parameters. This is trying to demonstrate that you can use a universal kind of hydrodynamic response, which will actually reflect in these different type of heavy ion collisions. If you measure the RIC and LC with different type of systems listed here, from the large size like lead collisions to small P-gold collisions at the RIC and LC. So this really demonstrates that the hydrodynamic expansions is actually a dominant physics actually drive the experimental measurements of these anisotropic flow coefficients. So from this, we actually like to extract the transport properties of the quark-gluon plasma, for example, the viscosities. Actually, you can see that here's a list of the work has been used this so-called Bayesian analysis to use multiple data and trying to incorporate both theory and experimental uncertainties into this extraction of the shear and bulk viscosity of the QGP. So here is a exercise actually done by the JetScape collaboration recently by fitting the charged particle multiplicities, mean PT, and also flow observables at both RIC and LC energies, trying to determine the size of the bulk and shear viscosities. The orange regions is about the 90% confidence level of the posterior distribution of extracted shear and bulk viscosity. As you can see, compared to the prior distributions we set in the model, you can see the data actually put a strong constraint on the shear viscosity near the temperature windows are about around 200 MeV. If you look at the different shape between the gray and orange band. So this shows you that with the precision hadronic measurements, we can actually constrain systematically the QGP viscosities in this, using these Bayesian techniques. Last but not least, I would like to also advertise that with this Bayesian analysis, we can also build a JetScape widget, which actually help you to build up your own intuitions about how observables changes with the model parameters. So you can feel free to go to this website or just click on this link on the slides. You can go to this widget page developed by the JetScape, and there are about 17 parameters you can actually tune within a reasonable physical range, and help yourself to build up intuitions what will be this parameter do in the model in terms of affecting the experiment observables like the particle multiplicities, mean PT, and the flow observables. So this will actually be a very intuitive way to help you to develop intuitions about what is viscosity do to the experimental observables. So I would really highly recommend you to check it out and play with it yourself. So now let me go away from the extensive study that we have been done in the last 10 years around this high energy limit, where we basically probing the quark-gluon plasma phase at the temperature along these temperature axes at mu b equal to 0. So we want to now go beyond that and now actually look at the heavy ion collisions at the finite chemical potentials. As I show you here, there's a list of the experimental programs currently is doing, as well as in the future, that is dedicated extensively to these finite mu b regions to do heavy ion collisions at the low energies. And this will help us to probe the QCD phase diagrams in this finite mu b area and study the nature of phase transitions at the large mu b, whether it's a first order phase transition or the smooth crossover, as the lattice QCD predict within this small mu b range. So we also would like to understand how is the transport properties of the matters changes as we go to large chemical potentials. So as you go to the low energies, there's a few challenges on the theoretical side trying to describe the heavy ion collisions. The first is that just purely from kinematics, as you collide heavy ion with lower energies, the Lorentz contraction between the two of the nuclei along the beam directions become less contracted. So if you compare 200 GeV versus 20 GeV, you can clearly see that the significant extensions of the nuclei in these beam directions. So this means that when these nuclei pass through each other, there will be a finite time for these two nuclei to interact in this light cone picture. It is indicated at this diamond area. So in the high energies, we usually approximate this diamond area to be a point-like interaction zone and only consider the dynamics after that. However, for the low energies, we actually need to go into details about what really happens in these interacting regions, because if you just do a pocket formula calculation of this overlapping time or the size of these overlapping regions, this can go to about 3 Fermi, which is about 1/3 of the lifetime of the total evolutions of heavy ion collisions. As you go down to say 7.7 GeV, that probe as at the relativist heavy ion colliders. So in order to go beyond the conventional Biot-King paradigm, where everything is considered as a highly boost Lorentz contracted, we need to go to really describe the three-dimensional dynamics in the low energies. So here is a partial list of the 3D initial condition models that people actually developed over the past few years, trying to use different ingredients of the theory to actually describe the initial three-dimensional distributions of energy densities in these low energies. As the two nuclei pass through each other, there's a finite interaction zones that matter keep interacting with each other as the two nuclei pass through each other, and this also requires to actually interface the fluid dynamic simulations with these overlapping dynamics, and this is usually now called dynamical initializations, which basically treat individual energy momentum as dynamical Thorstons to feed the hydrodynamic field as these currents. Here are a few frameworks that actually set up to do this for different type of collision systems from low to high energies. So here will be a cartoon of showing you what will be look like at 19.6 GeV heavy ion collisions. So we have two nucleus now is not infinitely Lorentz contracted. As they fly through with each other, initially it will have overlapping, which the system will continue to deposit energy momentum into the system. After that, the system will actually expand in 3 dimensionals with hydrodynamic equation motions. So we can view these dynamical expansions on the QCD phase diagram in terms of temperature and chemical potential at different snapshot of time. So initially on the upper panel, I show you the early time. You can see that if you look at the fireball in the middle rapidity on the central, you see the fireball initially just increases temperature, and gradually after 1 Fermi, you see that there's gradually more and more baryon deposit into the medium, which move the fireballs to the finite UV regions. So this what I call it will be the dynamic initialization stage, and you can also see the baryon doping in this stage as well. After the two nuclei pass through each other, the system will basically expand according to hydrodynamic equations, and you can see that the fireball basically just decreases temperature and traverse as some trajectories along these T and UV planes, mostly on these S over N equals to constant approximately lines on these in these trajectories. At the later stage, after 5 Fermi, you basically have a large portion of the fireball going through the phase transition below some switching energy density and start to switch to the hadronic transport approach. So you can also look at the fireball at the slightly forward directions, which were corresponding to the upgrade from the star X TPC. So you can look at the forward directions, which is indicated as these blue blobs in this QCD phase diagram. What you can see is that at the forward rapidity, the same energies, you will get a fireball probing a slightly larger mu-b regions, but the lower temperature regions in these forward directions. So now let me give you some results that we have been done with a simple three-dimensional model using the global geometry with the string deceleration models to distribute the energy momentum distributions in 3D in this initial stage. So the key ingredients is that we consider the incoming partons to collide within their rest frame. And then after they collide, we model their energy loss by a classical string decelerations, and then deposit energies along the string in this between them, as well as the leftover energy will be deposited at the string ends here. So let me show you that so the model actually takes a curve of parameterization of the energy loss in terms of rapidity of the incoming partons rapidities. So this is basically a curve parameterized by 3 parameters, trying to describe at which rapidities, how much rapidity will these parton lost in this pair of the parton collisions. So we fit this curve to the minimum bias proton-proton collisions at different energies, because at different energies, the proton come with a different beam rapidities, and you can actually use the PP results, multiplicity productions to actually fit this curve. So once you have this curve fit, you can now extrapolate to the other collision system, say the Dudron-Gold system, according to a global model. And here on the right-hand side is our predictions. Once we use the same central definition of Phoenix by triggering the multiplicity at the backward directions of the go inside, and you can see that this model do a decent job of predicting the multiplicity distributions of Dudron-Gold at 200 GeVs from these models. We can now go one step further to the heavy ion collisions, where we introduce additional parameter to basically consider that the multiple binary collision could be in terms of coherence, so that you don't need to. So not every binary collision will be effective in the heavy ion collisions to produce particles. So in that case, we actually use the central collisions as a tuning experiments, tuning data to tune these parameters. And then after that, the semi-peripheral will be the model predictions. As you can see that this model behaves reasonably well in terms of predicting the Phobos measurements as a function of the pseudo rapidity. So not only that, we can actually also take a look at the net proton distribution at first functional centrality from this model. And we can see that this model also do a decent job for the net proton distributions from central to semi-peripheral collisions in the Rickaby energy scan data. And as you can see that the star measurements at the current stage only limited to the middle rapidities, and the future measurements from BS phase 2 will help us to understand further constrain the rapidity dependence of the net proton distributions as well. So last but not least, we can also look at the individual identified particle productions. Here I show you these ratios between, say, k minus over pi minus as a function of root s, or k plus over pi plus as a function of root s, as you go from 200 GeV down to 7.7 GeV compared with the world data. And here on the middle panel is the particle versus anti-particle ratios, pi minus over pi plus, k minus over k plus, and proton, anti-proton versus anti-proton versus protons, and then also the multi-strangeness particle ratios. So, so in our case, the main ingredient in our model is basically we assume grand canonical ensembles when we switch from fluid cells into particles at the constant energy density. And we impose stranding neutrality conditions, and the electric charge is equal to 0.4 times the baryon density. With these two conditions are extremely important to help us to reproduce these identified particle ratios. For example, the electric charge is really important for us to get this ratio of pi minus or pi plus correct in this case. So now let me use the last 10 minutes to actually go a little bit away from the normal quantitative measurements analysis in the small chemical potential, but really go to really large chemical potential where we do not have the lattice QCD calculation for the equation state ready available. So the question we'd like to understand is trying to explore is in QCD phase diagram we will have a critical point and its associated first order phase transitions in the QCD phase diagram. So let's first assume that the fireball is actually near the critical point, but on the smooth crossover regions. This could be around 7.7 GeV where the rig is probing, but we are trying to look at the critical phenomena in this when the fireball is close to the critical point. So in order to model the critical behavior, we need several ingredients. So one is that we actually need a equation state that actually parameterizes the critical behavior as we go to some large chemical potentials. And this is being taken over by the best collaborations to develop a parametric equation state where a user can actually freely define the critical point in the T and mu B plane and its critical regions, the size of critical regions. And here I show you just basically the thermodynamic quantities for this equation state with the presence of a critical point. So with this critical equation state, we also need to understand the dynamics of the fluctuations when the fireball is close to the critical point. So there are two approaches on the market. One is called Stochastic Approach, where we evolve the stochastic noise explicitly together with the hydrodynamic equations. So schematically, the equation of motion looks like this, where the psi tilde is actually a fluctuating quantities which receive noise at every time steps from these C terms. So this actually has been adopted by a few groups in the world trying to actually understand the fate of the fluctuations in these heavy oscillations. Another alternative approach is called a deterministic approach, where we actually evolve the multi-point correlation functions in addition to the equation motions of the average variables. So the second approach basically is a deterministic because there's no randomness fluctuations in the equation motions. You always model the average values of either single point functions or 2-point functions in this approach. And this is recently developed by a few people, which is usually called hydrokinetic approach. So these two approaches are actually complementary to each other and have been carried out in a simplified dynamical framework. For example, here is a demonstrations that there's a stochastic approach using this numerical solver. You can actually reproduce the expected kurtosis of the 4 particle correlation functions at the equilibrium. And you can also go further to actually study the influence of that expansions in the simplified Biot medium. As you can see that in the equilibrium, the kurtosis is about minus 0.025 in the dip, and they actually reduce the strength in the dynamic expanding regions. So we would expect that in the expanding mediums, the kurtosis of the critical behavior reduced by about 50% if you look at these comparisons. On the right-hand side is the deterministic approach, where you can evolve the second 2-point function, which is the variance of the fluctuations, explicitly through its own equation motions. And this has been carried out through a Biot mediums as well as 2+1 dimensional mediums through these hydro plus formalisms. And the key feature is you can see that in the low frequency levels, these solid line indicate as these out of equilibrium dynamical evolution of these 2-point functions cannot catch up the equilibrium values. They actually become much slower as so-called critical slowing down when the fireball is close to the critical point. So last but not least, you can also expect that the experiments in heavy ion just don't stop at a certain energy. They keep pushing to the limits of this QCD phase diagram. For example, the star fixed target experiments can be carried out at the lowest as 3 GeV, and this is also overlapped with the future FAIR and NICA experimental programs in these large new regions. And what if, so the QCD phase diagram is actually interfacing with a first order phase transitions, then we actually start trying to look at what is the effects of softening and clustering in this fireball when it's inside this first order phase transition regions. So when we looking at the equation state, if you have a first order phase transitions, the easiest one is to actually do a Maxwell constructions between the two phases where you have a speed of sound to be equal to 0 in this mixed phase. And this will lead to a 0 speed of sound, or people usually call this softening around this equation, around this mixed phase in these low energies. So one of the signatures people thought have been thought is this the slope of the direct photon direct flow at the mid rapidity, and you will actually see dip structures as you go to these first order phase transitions, and this dip structure is reproduced by both just pure transport approach as well as the hybrid approach using hydro plus hadronic transport. In the hybrid approach, you do need a specific freeze-out criteria to reproduce the dip. If you use the conventional constant energy density one, actually the dip is very, is basically wash out. So this example or this signal is kind of elucidative, but it's not a smoking down to this softening of the equation state. And also in the unstable, in the first order phase transitions, when you have unstable region, instead of doing Maxwell constructions, you can actually have a meta-stable regions where the speed of sound goes to negative. And these will be the regions when the system go into these unstable regions, there will be so-called spin-order decompositions where instability can grow and generate a phase separation between the two phases. And this actually can be implemented in the hydrodynamic descriptions by introducing a surface tension terms with the gradients turns in here. And this has been first pioneered by these people here, and also Scott Pratt has recent updates on making these more correct formulations inside fluid simulations. But the key feature is that when you simulate with these surface terms, you will see that there's visible clusterings during these heavy ion collisions in this first order phase transition. And this is the features we want to look for as we go to looking at the experimental data, whether there's clusterings in the experiment that can show up in the experimental observables. So so let me basically end with a collection of figures that actually showing a intriguing non-monotonic behavior that has been measured in the star measurements in the BES phase 1. So here, basically, there's a ptosis where you see there are some hints of the non-monotonic behavior. So in the star paper, they claim this is about 3 sigma, about non-monotonic behavior as a function of S. There's also non-monotonic behavior about the light nuclear productions. As you see, there's somewhat bump structures in terms of the heavy light nuclear productions, as well as the slope of the V1 of the net protons. Of the protons, you can see there's a dip around similar collision energy regions. Last but not least, there's also the HPT radii difference also give you the non-monotonic behavior. So our field really need a consistent theoretical descriptions to explain really the baseline, as well as including critical phenomena to see whether all these different non-monotonic behaviors due to just the collision dynamics, or it's actually coming from the critical point. in order to actually explain this, the best collaboration in the DOE is actually take this task and trying to build a comprehensive framework to include all these physics in one framework, trying to model this. And here's basically a colorful workflow for this best framework, which can be which is able to do for this type of physics. And this is open to, this is an open source framework that can be accessed by any people over the world to carry out this analysis. And last but not least, there's also a next generation theoretical framework that will be is being developed by the JEScape, EScape collaborations in the US, trying to also include the real probes in these dynamics and being a full-fledged event generator for heavy ion, for high energy nuclear physics, for high energy communities. And I would advertise there's is a summer school in July that will help you to do some hands-on exercise of using these frameworks. If you're interested, just try to click on this link and apply for the school. So let me go to my summary. So I would say that the dynamical framework are very effective for us to help us to understand the dynamics of heavy ion collisions and help us to learn the properties of heavy ion of the QGPs. So it basically bridged the first principal calculation from lattice QCD data to the experiments and help us to understand the various principal properties of the QGP and now in a baryon-rich environment. Last, we also talk about there's emergent theoretical description progress on trying to understand critical behavior as you go to a critical point, and this will help us to combine with the RIC BES phase 2 data, trying to understand the phase structure in a quantitative way in the near future. So thanks.
Thank you, Chun, for this very nice overview. So we have 4 questions in the chat, and I would like to ask the people who asked the question to turn on their camera, and in addition to their mic. So the first question is by Hesam. Hesam, can you ask your question, please?
Yeah. Hi, thanks a lot for this nice overview. On your slide 9, you gave us some information about how the having or not having the viscosities can have different.
I think
or 8, I think, yeah, right.
Yeah.
So I was wondering, because in the left-hand side, we just wrote shear viscosity. I was wondering if in these two simulations, you only consider shear viscosity, or it has also.
So this simulation I show you only have shear viscosity included. So that's basically the difference.
And does it change if we have also bulk viscosity?
It will change somewhat, but the bulk viscosity usually act as a resistance to the whole radial expansions. So you will see that the fireball actually will expand slower, but the lives longer if you have bulk viscosity in there.
Okay, next question by Yogesh Kumar. Yogesh, can you ask your question, please? Okay, then we go to the next question. Gabriel, can you turn on your camera and ask the question?
Hi, Chun.
Yeah. Hi.
You hear me?
Yes.
Yeah.
Okay. Thank you for the nice talk. So I have a somewhat naive question. So is there any intuition that do we have any do we now have any intuition about the effects of particle or energy diffusion coefficients to the anisotropic observables and
so for the charge diffusion, I think it's found that we find something that it actually have some influence on the, say, proton versus anti-proton flow. But the particleization, there's a so-called off equilibrium corrections, which also is very sizable to that correction. And there's a recent study by Scott Pratt, and they actually trying to understand the charge diffusion through charge balance functions. And I think that would be also a very good observable trying to understand or extract the charge diffusion constant in there, in addition to the regular flow observables.
Okay. Then Uli has a question.
On slide 18, can you briefly explain why the baryon doping is delayed relative to the initial heating of the matter?
So yeah, so in this case, I think most of the baryons, not all of them, but most of them are still at the string ends. So if you look at, say, like a time light cone picture, the string end usually is later at later than the energy depositions. So that basically causes somewhat delay. So usually you only see some energy deposition in the middle of the string, heat up the system, and then you have the baryon.
So that's caused by the string-like modeling of the
yes, that's basically could be just a model dependent picture here based on the string model.
Any other questions, folks? You can also raise your hand. Well, I don't see any. Then let's thank Chun again.
Yeah, thank you.
And let's go to the next talk by Ali, I think.
Yes.
Ali, where are you?
I'm here.
There you